Okay, so we're recording. Welcome back, everybody. This is the 17th week of class and the final week of class before exams next week. So the end game is we're meeting today for lecture. We're meeting for Wednesday, meeting on Wednesday for lecture as well. But after that, there's nothing going on except for the final exam. Okay? So homework number 16, remember, is due this Wednesday. So that's due in 2 days. Homework number 17, which will be the very last assignment, that's up here on the board. That's going to be due next Wednesday, which is also the day of the final exam. Okay? So that'll be the last assignment. So part of homework 17, as usual, is a worksheet. So make sure you get a copy of that. Also, while you're up here, get a copy of the final exam review problems. These are also up on Canvas. Has anyone taken a look yet at the review problems? You should. So I'll be posting the solutions to those review problems by Friday of this week. So start working on those this week, and the solutions will be up on Friday. So speaking of that, we don't, again, have any official lab meetings this week. So you don't have to come in for lab, and it's not for credit. But if you'd like to come in at the usual times, you can, just to work on these problems. And I'll be around to help you and answer any questions you might have. Okay? But it's just optional, it's not for credit. So any questions on that? All right, so in that case, we're going to jump back into the lecture. So if you recall, the last thing we did last week was derive this formula right here for what's called magnetic energy density. So we did a derivation, we're getting sort of into the weeds there. Let's look at the big picture. The big picture is whenever you have an electric field or a magnetic field, so E or B, there is going to be energy in the space that the field occupies, okay? So we can talk about the energy per unit volume in that space, which is called the energy density. And we have a different formula for the electrical energy density. That applies when there's an E field present, and the magnetic energy density, which applies when there's a B field present, okay? So if you recall, way back in, I think, chapter 9, if I'm not mistaken, we derived this formula for electrical energy density. And again, this tells you the energy per unit volume that's present when there's an electric field. We got this derivation from thinking about a parallel plate capacitor, which has an E field in between the plates, and the energy per unit volume that will be present in between the plates. But we saw that this actually applies more generally, just whenever there's an E field. So this electrical energy density, given by U sub E, is equal to epsilon naught times E squared. That's the strength of the E field squared, divided by 2. What we just derived last time was the magnetic energy density. And again, we derived this formula in a specific case, which was thinking about a solenoid, and the fact that when you have a solenoid, there is a B field inside of it. But this, again, applies more generally. So the magnetic energy density, which is U sub B, is equal to B squared divided by 2 times mu naught. Okay, so we have the constant epsilon naught appearing in the electrical energy density. Remember, this is 8.85 10 to the minus 12 coulombs squared divided by newtons meters squared. And then the constant mu naught appears when it comes to the magnetic energy density. And that's 4 pi 10 to the minus 7 Tesla meters per amps. And these are called the permeability of free space for mu naught and the permittivity of free space for epsilon naught. But those are fundamental constants that come up in our equations. All right, so that's the formula, and that's what it looks like alongside a previously derived formula. And again, big picture is electric fields and magnetic fields contain energy. And this is how we can think about that energy. So I thought we could take that result and do an example with it. Okay, so here we have the strength of Earth's magnetic field. This is something we see pop up from time to time in our problems. Again, the magnetic field created by the Earth and the electrical currents going on inside of the core of the Earth is kind of complicated, but it has sort of an average or typical value, which is about 5 times 10 to the minus 5 Tesla. All right, I gave you again the mu naught and epsilon naught constants here. You might need those. So the first question is, calculate the energy density of Earth's magnetic field. So joules per cubic meter. Given the strength of Earth's magnetic field, what is the energy density? And then as a follow-up, how strong would an electric field have to be in order to give you the same amount of energy density? Okay, so for the first part, just straight using that result we derived for magnetic energy density. In the second part, you want to bring in the electric energy density formula and compare. All right, so take a few minutes, see what you get for this, and then we'll go through it together. All right, I see that some of you got this. Does anyone have an answer for the first question? So given that the B field has this strength right here, what is the magnetic energy density? What are we getting?
1.99 times 10 to the 1.
Not quite getting that. Anyone else? Yeah, so about, if you round it to the nearest power of 10, it's like 10 to the minus 3, roughly. So let's do that calculation real quick. For magnetic energy density, this is lowercase ub. The formula derived was B squared. That's the strength of the B field squared divided by 2 times mu naught. And this is going to come up in some stuff we're going to do later. So for Earth's magnetic field, we're going to take the sort of average value of 5 times 10 to the minus 5 Tesla, then square it, and then divide by 2 times mu naught, which is 4 pi 10 to the minus 7 Tesla meters per amp. So I'm not going to go through the whole unit analysis. You can show that this does work out to the expected unit of joules per cubic meter. And again, someone said it already, but 9.95 10 to the minus 4 is the result you get. And nearest power of 10, that's about 10 to the minus 3 joules per cubic meter. There's about a millijoule of energy per cubic meter of space because of the fact that Earth's magnetic field has the value it has. Okay? So the other question here, the follow-up was, okay, let's take this as our energy density. What would an electric field have to be? How strong would an electric field have to be in order to produce that same amount of energy density? So what we'll have to do there is use the formula for electrical energy density, which says UE is a half times epsilon naught times E squared. And in this case, we're solving for E. So here we have E squared equals 2 times UE divided by epsilon naught, just like that. And then we'll just square root to find E. All right, so here's what we have. 2 Now, what we're putting in here is our energy density that we found earlier, which is 9.95, 10 to the minus 4 joules per cubic meter. Okay, and then we're dividing by epsilon naught, which is 8.85, 10 to the minus 12. Units are weird again, coulomb squared divided by newtons times meters squared. And then we're square rooting this whole thing in order to solve for E. All right, what did we all get for this? What's the result of this calculation?
1.5 times 10 to the negative 4.
1.5 times 10 to the minus 4 newtons per coulomb, right? I think if you, sorry, 10 to the positive 4. That's not minus 4.
Oh, wait.
Yeah. So yeah, 1.5 10 to the 4 newtons per coulomb to produce the same energy density as Earth's magnetic field. Okay, so that's just a little practice using these formulas. Again, they're going to come up later once we start talking about electromagnetic waves. Okay? So we good so far? All right. Actually, another place these formulas are going to come up for electric energy and magnetic energy, that is the energy stored in E and B fields, is here. We have something called an LC circuit. Okay? So let me remind you, we already know what a capacitor is. We've worked with these things for a long time. We just introduced last week this circuit component called an inductor, which we give by the letter L, okay? Because it has this feature called inductance, which is denoted by the letter L. So if you have a circuit with nothing more than a capacitor and an inductor, that's an LC circuit. All right, so let's say that we start off with this circuit and charge on the capacitor. So at t equals 0, we have plus or minus Q naught on the plates of the capacitor. It's fully charged, okay? But what we do is close the switch at t equals 0. So we'll connect that capacitor to the inductor, and then we'll see what happens. Can anyone guess what might start happening once we close the switch? So initially, we just have charge on the capacitor, no current. What's going to start happening once we close the switch? Yeah, so current might start flowing, okay? So let's try to understand how current flows and how charge moves around within this circuit. And what we're going to use, as always, is, well, how do we analyze what's going on in the circuit? Okay, but that's Kirchhoff's laws, right? We're going to basically apply Kirchhoff's laws to this circuit that you see here. Make sense? All right, so in particular, we're going to apply the loop rule, okay? You guys remember how this works? All right, can anyone state what the loop rule is? Kirchhoff's loop rule. Yeah, so we take a complete loop around the circuit, and the sum of the voltages will equal 0. It's actually pretty simple here, because you just go across the capacitor, and then you can go across the inductor, and then the voltages sum to 0. It's pretty straightforward. Okay, so we close the switch. Now we have a complete circuit, and now some current can start to flow off of the plates of the capacitor, which has plus Q on the top plate and minus Q on the bottom plate. All right? And here's what Kirchhoff's loop rule looks like. Let's start by going across the capacitor. What's the voltage across the capacitor? Q over C, yeah? Q over C. What's the voltage across an inductor? Does anyone remember this? We did this last week. It's not L times I, it's L times the derivative of I. Okay? So here's the loop rule. Q over C when we go across the capacitor from the negative to the positive plate. And then L times the derivative of I with respect to time going across the inductor. And there's also a negative sign here because the voltage across an inductor, if you remember, opposes changes in current. So that's what this negative sign kind of does for us. All right? So what we're going to do is try to solve that equation right there. Because if we can solve it, we can understand how current and charge change as time goes on. Okay? Okay, so the first thing I want to do is come up with a substitution for di by dt, and this is what I'm thinking, okay? So di by dt, that's the derivative of current with respect to time, right? But what is current in the first place? Current is the derivative of charge with respect to time. So essentially what I'm doing here is I'm putting the derivative of charge with respect to time in for the current right there. But not only that, I'm introducing a negative sign. And the reason for that is, as the current starts to flow, we're losing charge, okay? That's the reason for this relative negative sign in the equation, okay? So a more simple way of saying that is the derivative of the current with respect to time, that's di dt, which appears here, can be thought of as the second derivative of the charge with respect to time, but with that negative sign on the front, okay? So why don't we just go ahead and take that and sub it in right there. The reason is I don't want two different variables to think about, current and charge. I just want to think about one variable at a time. So this helps us do that. So subbing that into the loop rule equation, here's what we get. So I have a negative sign here and a negative sign here, overall positive. Second derivative of q with respect to time. And then all I'm going to do is divide out this L, so that instead of a C here and an L here, I'll just have an LC on the bottom of this term right here. So we have the second derivative of q with respect to time plus q divided by LC. And when we add those together, we get 0, because again, this is just the loop rule equation. So the summation of the voltages goes to 0. We just made a substitution here, all right? So we're just going to do a little bit of manipulation to that equation, okay? All I've done here is I've rewritten the differential equation that was on this line to say that, let's have a new variable. Let's call it omega. And just by definition, I'm going to call omega 1 divided by the square root of LC, okay? So we have 1 divided by LC right here. That must be omega squared, right, to get rid of the square root. So I'll show you why I'm doing this in a second, but this is a substitution you could make if you just define omega in this way, right? Now, looking at this equation right here, we have the second derivative of q with respect to time, plus some constant, which I'm calling omega squared, times q equals 0. Can anyone sort of recognize that? Maybe if you think all the way back to physics 45. You have seen something like this before. What is it? Okay, so it's not quite a wave equation, but it's a simple harmonic motion equation. It's describing something that's oscillating back and forth. You guys remember the mass on a spring system from physics 45? That had the same exact differential equation, more or less, except in that case we were talking about the position of a mass on a spring. In this case, we're talking about charge. But this is describing charge oscillating, sloshing back and forth, okay, in this circuit. So let me just show you what the solution to this is, okay? My claim is that if this is our differential equation, the solution for charge looks like this. Q as a function of time, that is, how much charge is on the capacitor as a function of time, equals Q naught, that's the maximum value that we start at, times cosine omega t. And of course, cosine is a function that just oscillates up and down. So this is describing an amount of charge that's oscillating up and down between positive Q naught and then negative Q naught. All right, so I'm going to show you that that actually works out. All right, so here we go. My claim is that this solution is correct. Q of t equals Q naught cosine omega t. Okay, let's just work through real quick. What's the first derivative of this guy? And then what's the second derivative? These aren't too hard to do. And then we'll see that it works to solve the differential equation that we're initially given. All right, so if you have cosine omega t, what is the derivative of that with respect to time? It's going to be negative sine. And then what else happens? I have an omega in there. What happens to that? Comes out to the front. So minus Q naught omega times sine omega t. Do we agree? Okay, if I wanted to take a second derivative, I would need to now take the derivative of that again, right? What would that give me? Yes, and the negative sign stays, q naught, and then I have a second factor of omega coming out when I take the second derivative, so overall it's omega squared. And then sine goes to cosine, right? Okay, well the differential equation we had was the second derivative of q with respect to time plus omega squared times q equals 0. Does that work? Let's see. The second derivative is minus q naught times omega squared times cosine omega t. That's just the second derivative right there. And then if I add to that omega squared times q, which is this, q naught cosine omega t, does that equal 0? Yes, I'm just adding two completely opposite terms. So this shows that that's the solution to the equation, okay? So in an LC circuit, what do we have? We have charge on the capacitor, again, oscillating back and forth between plus q and minus q over time. But we can take it a step further. If that's the solution for the charge, what's the solution for the current? Remember, I, the current, is minus dq by dt. In other words, it's just the negative of this right here, okay? In other words, it's q naught times omega times sine omega t. And this thing, q naught times omega, we might call that I naught, because it's like the maximum amount of current that appears in our circuit. If q naught is the maximum amount of charge, I naught represents the maximum amount of current. Okay? And that's basically everything we need to know about this circuit, right? It's got a charge which oscillates back and forth, and it's got a current which also oscillates back and forth. Okay? Does someone have a question over here?
Yeah, if it matters if it has a negative sign or not.
Yeah, because the reason for that is as the current starts flowing, we're losing charge off the capacitor plates. So that's the reason for that. Okay, but now we've shown the result, and we've got the solution for the charge and the solution for the current. Okay, here they are. And remember, I naught is q naught times omega. Okay? That's pretty much everything we need to know about charge and current in an LC circuit. So, we had to go through the derivations, but the result is pretty straightforward. Each one just kind of oscillates according to a sine or a cosine function. Okay? So let's take a closer look at the solutions and maybe start to think about them graphically. Okay? So that's the next step. We have an LC circuit. So first of all, in the LC circuit equations, we have omega. Omega is appearing inside the sine function and the cosine function. The way you want to think about omega is that's what we call the angular frequency of the oscillation. It's telling you how fast does the charge oscillate, how fast does the current oscillate, okay? And again, that omega is 1 over the square root of L times C. So if you know the inductance, L, and you know the capacitance, C, you automatically know the frequency that your circuit is going to oscillate at, okay? So let's take a look at the graph of each one of these functions, starting with Q of t. So what is that? It's just some kind of maximum value times cosine omega t. We know what the cosine function does, right? If the input of t is 0, then we start at the maximum of the cosine function. So we're at plus q naught. Then we go to 0, so now there's no charge on the capacitor. And then we go down to minus q naught. So what is that describing here? It means you've started off with, on the top plate, positive charge and negative charge on the bottom. But now it's flipped around the other way. The charges on the plates have reversed. Then the charge goes back to 0, and then it goes back to the starting point. And then that just repeats over and over again. All right? As far as the current is concerned, it looks like this. This is given by the sine function. So sine function starts at 0, goes up to a maximum, comes back down to 0, goes down to this minimum, and then back to where we started. So one thing I want you to notice is that these two graphs are kind of offset from one another, right? They're not both a cosine function or both a sine function. One is a cosine function, the other is a sine function. And one feature of cosine and sine is that they're offset from each other by 90 degrees or a quarter of a cycle. So in other words, let's just like kind of draw a straight line right here where I have 0 charge on the capacitor plates. At that exact moment, when there's no charge on the capacitor plates, I see that my current is at a minimum or at a maximum. Okay, so when one function is at 0, the other function is at a minimum or a maximum, meaning when you've got no charge on the plates, you have the most amount of current, okay? And vice versa, right? When I have no current, that's I going to 0 here, that means the charge on the plates is either at a maximum or a minimum, okay? So, got that all clear? So let's now bring in this idea of energy in this circuit, okay? We know that the more charge is on the plates of the capacitor, the more energy is stored within the capacitor in its electric field. And the more current that's running through the inductor, the more energy the inductor is storing in its magnetic field, okay? And what we're seeing happening is basically energy is just sloshing back and forth between being stored in the capacitor and then stored in the inductor, just sloshing back and forth at some frequency, okay? So let's recall some formulas that we derived. The energy stored in a capacitor, this is something we went over a long time ago, is equal to Q squared divided by 2C. The energy stored in an inductor is L times I squared divided by 2. We obtained this result last week on Wednesday, okay? So the idea here is we can sort of apply conservation of energy. The total energy in this circuit is going to be conserved. It's just that the form it takes on is going to change over time. It's going to sort of oscillate between, again, being stored in the capacitor and then in the inductor, back and forth like this, okay? So what did we just show through those graphs a second ago, right? When there's a maximum amount of charge, there's 0 current. Okay, and when there's a maximum amount of current, there is 0 charge, right? So because of that fact, we have sort of two different ways of thinking about the total energy in this circuit, right? The total energy in this circuit, of course, is just the energy that's in the capacitor plus the energy that's in the inductor. If we just add those together, we get the total. All right, but we can express this sort of two different ways, okay? One way is like this. We can express it in terms of the maximum charge. So remember, when we have the maximum amount of charge, we have 0 current. And that means we have no energy stored in the inductor, right? So when charge is at a maximum, all of the energy is just in the capacitor. In which case we can write it as Q naught squared. That's the maximum charge squared divided by 2C. Okay? And then just flip that reasoning around. Remember, when current is at a maximum, we have no charge. So when current is at a maximum, there's no energy stored in the capacitor. Okay? And that means all of the energy is stored in the inductor, in which case we can write it as L times I naught squared over 2. So you can write it either way. These are both valid ways of writing the total energy. They give you the same answer, but thinking about it in these two different ways is sometimes useful, okay? So one thing I should mention here real quick is that the assumption I'm making is that there's no resistance in the circuit, which is not exactly realistic, right? So a more realistic circuit, which we don't have time to go over in this class, would be something called an LRC circuit, where we introduce some resistance alongside the capacitor and the inductor, okay? But assuming no resistance, it just oscillates back and forth indefinitely, never stops, okay? If there is resistance, then the oscillations die out over time. Make sense? All right, so let's do an example. Actually, no, let me show you an animation. Hopefully makes this idea a little bit more clear, okay? So you can find this animation on the slide if you click the link. So if you access the slides from Canvas, you can watch this again. But this is a nice animation of an LC circuit. And before I play it, let me just note some things to watch out for. So one thing that's going to be shown are the charges on the capacitor plates, positive and negative. Also going to be shown is the E field inside the capacitor, which of course points from the positive to the negative plate. We also are going to be shown the current that's running through the circuit and creating a magnetic field in the inductor, okay? And we'll see the B field lines, the magnetic field lines within that inductor. So what's going to happen is at one moment, the E field is going to be at a maximum, meaning the charge is at a maximum on the capacitor, and all the energy is stored here. And then charge is going to begin to flow through the circuit in the form of a current. And then when the current is at a maximum, we're going to have the largest B field here and no charge on the capacitor here. And then that's just going to repeat over and over again for many cycles. Okay? You see that? The capacitor is charged up, now the inductor has all the energy. Now the capacitor has all the energy, now the inductor has all the energy. Just sloshes back and forth.
Why does the direction of the current switch?
So, I mean, it just comes out of the math, but an important thing to make that work is the voltage across an inductor has a little negative sign. It opposes changes in current, and it would not work out to the solution we got without that negative sign. Yeah. Okay, so I just wanted to start you thinking about energy oscillating between E fields and B fields like this, because we're about to go over electromagnetic waves, where this is a very important concept to understand an electromagnetic wave, okay? So this is kind of a warm-up for that. But before we get into that, let's do a few example problems, just work with the equations that we derived, make sure we know how to deal with them, okay? So it's really not so bad once you get past the derivation. All right, so here's what we have. We have a circuit where we have an inductor. L is 75 millihenries. So that's called the inductance of this object right here. We have a capacitor, which is 1200 picofarads in terms of its capacitance. And then we also have a battery. Let's say it's just the perfect ideal battery with an EMF of 500 volts, okay? So we have a switch, so we can control the flow of current. The first thing we'll do is we'll start with the switch open, and there's no current here, there's no charge here to start off, but after that we'll throw the switch to position A. And what happens is we're just connecting the battery to the capacitor, but the inductor is left out of this circuit, right? So the first question we'll ask is, what is the resulting charge on the capacitor? Right? We throw the switch to position A, we just charge up the capacitor. So we want to know how much charge we get, okay? Then what we do is we throw the switch to position B. What do we do then? We're taking this charged capacitor and we're connecting it to the inductor, which is exactly the scenario that we've been going over for this LC circuit, right? So at that point, as we know, charge is going to slosh back and forth, current is going to slosh back and forth within the circuit, and there'll be some kind of frequency for that oscillation, okay? So what we'll do is we'll calculate what that frequency is in hertz. Then we'll answer these two follow-up questions. What is the maximum current in that circuit? So what is the peak value in amps, the amount of current that's flowing in that circuit? And what's the total energy in that circuit? Okay? So here, we'll start with the first question. This takes us way, way back to the capacitance chapter. Do you guys remember, if I just connect a capacitor to a battery, there's really nothing else in that circuit. How do I calculate the charge that forms on the capacitor? You guys remember? Yep, it's just going to be the voltage of our battery times C. That's going to give us the charge, okay? So that's our first calculation. So this will be our maximum charge, by the way. This will be what we call Q naught in our equations. Q naught is epsilon, that's the battery voltage, times C, that's our capacitance. Okay, the battery voltage was 500 volts, and the capacitance was 1200 picofarads. Do you guys remember pico? That's a unit prefix, 10 to what power? That's going to be minus 12, yeah? And do you guys remember what a farad is in terms of other units? It's a coulomb per volt. That's a useful way to think about it. It's coulombs per volt. Okay, so we work this out. It comes out to exactly 6 times 10 to the minus 7 coulombs. Okay? So that's how many coulombs of charge we end up with when we connect the capacitor to the battery. Okay? And that's going to be useful later. That's our Q naught value. Next, let's find this. Let's find the frequency of oscillation. So again, the circuit itself is oscillating in terms of the charge that the capacitor holds and the current that's flowing through the wires. There's some frequency associated with that. That's where omega comes in, okay? Omega is 1 divided by the square root of L times C. For an LC circuit, the frequency that it oscillates at just depends on the values of L and C. So, in the case of L, we had 75 millihenries. So that's 75 10 to the minus 3 henries. For the capacitor, again, we had 1200 picofarads, or 1200 10 to the minus 12 farads. Then we take the square root of that, and then we take the inverse of that. Okay. So I'm just going to tell you something about these units, okay? Whenever we see omega, what unit are we thinking is going to come out? It's radians per second, okay? This is slightly different from hertz. Hertz is cycles per second. This is radians per second. The difference between the two is a factor of 2 pi, okay? So if you do this calculation, it comes out to 1.054 times 10 to the 5 radians per second. Now, what should I do to change that to cycles per second? Yep. Where does the, yeah, so there's a 2 pi, but does it go on the top or on the bottom? Yeah, I got to divide that because I have 2 pi radians on the bottom for every 1 cycle. I want radians to go away and have cycles per second, okay? Which is another way of saying hertz, right? Cycles per second is the same as hertz. So this is 1.68 10 to the 4 hertz. So this circuit will oscillate through 1 complete cycle at this frequency, 1.68 10 to the 4 hertz. So that's very, very fast, right? That's like every second, about 16,800 cycles, okay? All right, so next question. What is the maximum current? All right, so for this, again, we're going to just use a result that we derived. The maximum current is what we call I naught. It's related to the maximum charge in a pretty simple way. It's just omega times Q naught, right? So you take the maximum charge Q naught multiplied by omega, which is the angular frequency, then you get the maximum current. So let's put in what we know. Omega, that's right up here, is 1.054 10 to the 5 radians per second. And it has to be omega in radians per second, not, this is what we would call F, actually, in hertz, okay? So Q naught is 6, I actually forgot to carry over the sig figs. We have 4 sig figs on that, right? 6.000, 10 to the minus 7 coulombs. Okay, so if you work it out, do the calculation. You get coulombs per second as your unit. You see that? And coulombs per second is the same as amps. So this is 6.32 10 to the minus 2 amps as our maximum current. Okay? And I believe there's one last question here, which is, what is the total energy that's sloshing back and forth within this circuit? Well, remember, we can write it two different ways. I can think of the total energy as being 1/2 L times I naught squared. That'll work. I can use this maximum current and the value of L, or I can do Q naught squared over 2C. So whichever way I choose to go, I'm going to get the same result, okay? Which way do you want to do it? Let's do that. Okay, so I have 6.000 10 to the minus 7 coulombs. We square that, divided by 2 times 1200 times 10 to the minus 12 farads. So you can show, if you do the calculation, this works out to 1.5 10 to the minus 4 joules. So that's the total energy in the circuit. All right? So any questions? Hopefully, again, once you have the results derived, it's pretty straightforward to use the results. Any questions? All right, I'm going to ask you a question about an LC circuit. I want you to work on it, and then we'll move on to electromagnetic waves. Okay? So let's say that you want to construct an LC circuit that oscillates at a frequency of 440 hertz. You have an inductor, which has an L value, which is already determined, 7.5 millihenries. The question is, what capacitance do you need to get the desired frequency? So this is kind of a practical issue, right? You're trying to design a circuit that oscillates in a specific way, at a specific frequency. Well, you're going to need to pick the right values of L and C to achieve that. So in this case, we're imagining L has already been determined for us. We want to find the value of C that's necessary. Okay? So take a few minutes. Again, you're going to use the formula for the frequency of the LC circuit here, and you should be able to find C. So try to get it. When you're doing this problem, just make sure you're careful with the difference between omega and tau, right? Very good. We're seeing some people are getting the answer. Should be getting about 17.4 microfarads. All right, let's just go through the calculation real quick. So first of all, for an LC circuit, omega, which is the angular frequency in radians per second, is 1 over the square root of L times C. But I want to also point out that omega can be thought of as 2 pi times f. Okay, so omega in radians per second, let me just write that down, versus f in cycles per second, I have a relative factor of 2 pi. Okay? So we're just going to take that now and try to solve for C. All right, so let's square both sides to start off because I have a square root here. So I have 1 over LC equals, now I'm squaring all of these terms. So 2 squared is 4 times pi squared times f squared, right? And if I go ahead and solve for C, C is equal to 1 divided by 4 pi squared times f squared times L. Okay, that's just how it works out. So now we'll put in what we know. C is equal to 1 divided by 4 pi squared. Our frequency f is 440 hertz, so that's 440. You can think of that as inverse seconds. We're squaring that guy. And then we have L, which is 7.5 millihenries. That's 10 to the minus 3 henries. Okay? And what you get is 1.74, 10 to the minus 5 farads as a result of that, which we can also think of again as 17.4 microfarads. Okay. So one thing just to be careful of, now that the units are getting kind of tricky, is if you do a calculation, just make sure everything is in SI units before plugging the numbers in, and you can be sure that what comes out is the relevant SI unit. Okay? So things like, millihenries, for example, just write that as 10 to the minus 3 henries, and you can't go wrong. All right. Any questions on that? That was our short detour into LC circuits. So now we're going to move on to the next topic, which is electromagnetic waves. And we're going to stay on this until the end of the semester. This is the last topic. Okay. I'm going to start by showing you an animation that I showed you on Wednesday of last week. You remember how a changing B field gives you a changing E field, gives you a changing B field, and so on? I'm just going to show you that one more time because it's really important to understand this idea. But after we do this, we're going to get into some of the math behind electromagnetic waves. Okay, so this is a recap. We've seen this before. I want you to think of, at the same time, Faraday's law, which, if you think about what it's telling you, says a changing B field produces an E field. Because we have the derivative with respect to time of the magnetic flux, that's B dot dA on this side. And then we have the integral of E dot dL on this side. So in a nutshell, you can think of that as the change in B here, giving you this E field on this side. Okay? Whereas if we look at the Ampere-Maxwell law, if you remember that, this basically says that a changing E field produces a B field. Okay? So this is the formula that we derived last Wednesday. So the example I gave you to sort of visualize an electromagnetic wave being produced is this. We have a rod with some alternating current on it. So imagine the current is just sloshing back and forth, up and down along this rod. Okay? And this is typical of what you would use to, say, create a radio wave, to transmit a radio wave into the space around you. But as we're going to see, this is much more general. Every electromagnetic wave can be thought of in this kind of sense. Okay? Even the light that you see right now. So going through this again, we have the current. Let's say for the moment the current is going up. So we know how there will be a B field looping around this wire, and the direction is given by the right-hand rule. Okay? So we have that B field, which I'm going to call B naught, like this. Okay? But what we imagine is that the current flips around because it's an alternating current. In one moment it's going up, the next moment it's going to be going down, so now we'll flip it down. And of course that flips the direction of the B field in the opposite way, right? So current going up gives you this B field, Once it flips to down, it gives you that B field. So now what we have is a changing B field. And in particular, I just want to focus on this region right here. There's a changing B field, which is creating some kind of changing flux, basically through the surface of the screen right here, okay? So that means, as a result of that, according to Faraday's law, because we have this changing B field, we're going to get an E field. And that's going to produce a loop like this that goes through this loop. We'll call that EMO, okay? So then, we'll just imagine the current flips once again, because this is just going to continuously happen. The current's now going up. All right, so now the B field here flips back the other way, and that means now this E field flips. And now we have a changing E field in this region over here, which gives us, according to the Ampere-Maxwell law, a B field, okay? And just imagine another cycle. The current flips back to down, so all these directions flip. Now, in this region over here, we have a changing B field. That gives you an E field. And the current flips again, all these directions flip, and now we produce a B field. And this just keeps happening, okay? So what we call this is an electromagnetic wave, okay? You have a wave that's being sent out away from its source, which is this oscillating charge right here. And that wave, we say, is propagating or traveling to the right in this direction, okay? What is the wave made out of? What does it consist of? It just consists of electric fields and magnetic fields, which are oscillating back and forth, okay? So that's fundamentally what an electromagnetic wave is. It's a pattern of oscillations in electric and magnetic fields that is moving through space, okay? So it's not just that you have E fields and B fields, which are oscillating, but those oscillations are going somewhere. That's why we call it a wave. It's traveling somewhere. Just like a wave, you know, crashing into the shores, heading towards the shore, right? So what we're going to see is, I gave you this example of an EM wave, an electromagnetic wave, being produced by alternating current in a rod, okay? We're going to see that if you want to be as general as possible, all EM waves are produced by electric charges which are accelerating in some way, okay? If you got an electric charge and it accelerates, it's going to give off an electromagnetic wave, okay? That's a general feature of our universe. Okay, this can obviously get kind of complicated. So I'm going to stick to sort of a specific case, which is, let's say our charges are oscillating sinusoidally. In other words, let's say in the example I just gave you, the charges in the rod oscillating up and down. Let's say that's given by a sine function, okay? If that's the case, then the E and B fields that are resulting in this electromagnetic wave are also going to be given by a sine function. So that's the example we're going to stick to, okay? Just sine waves, all right? We all know what a sine wave looks like, right? This oscillates up and down according to that familiar shape, okay? But one feature that I hope you picked up on from what I just showed you is that the E field direction, the B field direction, and the direction the wave is going are all perpendicular to each other, right? In the example I just showed you, you had the B field kind of going in and out of the page like this. You had the E field going up and down like this. And you had the wave traveling to the right like this. All of those directions are perpendicular to each other. That's a general feature of electromagnetic waves. That the E field, the B field, and the direction the wave is going are all perpendicular to one another. So here is a picture of just that sort of thing happening, okay? So this is showing us an animation of an electromagnetic wave, EM wave, moving in the positive X direction. So it's pretty clear just from the animation which way it's going, right? It's moving along the X-axis. In this case, we have the E field, which is oscillating up and down along the Y-axis. So you can see that the value that the E field takes is oscillating up and down. So sometimes it's at a maximum, sometimes it's at a minimum, sometimes it's at zero. At the same exact time, you have a B field, which is oscillating this way along the Z-axis, and it's the same deal. Sometimes it's at a maximum, sometimes it's at a minimum, and sometimes it's at zero. It just looks like a sine wave, both in terms of what the E field is doing and in terms of what the B field is doing. And that wave is going along the x-axis. Okay? You have a question? Okay. So, and again, it's kind of there's a lot going on in this picture, but hopefully you see some of the fundamental features of an EM wave. All right, so now we're going to get into some of the math. Like, that's a good mental picture to have, but what are some equations that describe an electromagnetic wave? That's what we're about to get into. So, before we get into those equations, I'm going to have to just define some things for us, okay? What are some of the quantities that go into the equations, and what do they mean? So these are just some basic definitions, okay? So what you see here, and we're going to use this picture as a reference, is an electromagnetic wave moving in the x direction. Just like in the animation I showed you, except it's not an animation, it's just like a snapshot of that wave, okay? Now, we have the E field going up and down along the y-axis, with the B field oscillating along the z-axis. And the first thing I want to define is what are called the amplitudes, okay? The amplitudes of the EM wave are just the maximum values of E and B, right? So if you look at the wave as a whole, the E field sometimes peaks. The value that it peaks at is what I'll call E naught. Same with the B field, that peaks at some point. We'll call that maximum value B naught. And together, those are what we call the amplitudes. The maximum values of those fields are the amplitudes. Okay, we kind of already know what frequency means, right? We've seen this before. The frequency is just the number of oscillations per unit time that the wave undergoes. So again, let's say we're thinking about the electric field, right? It's going to go to 0, it's going to reach a peak, back to 0, then to a minimum, and then back to where you started, right? So it has sort of a cycle of oscillation, right? The frequency is just the number of oscillations per unit time. We can measure that in hertz, right? So an electromagnetic wave has a frequency which we can measure in hertz. And related to that is something called the angular frequency. So they're pretty much the same thing. They're telling you the same information, which is how fast is the wave oscillating. The only difference is one is measured in hertz, the other is measured in radians per second. So we just went over this difference, right? Omega is 2 pi f. Okay, so we can use either description, depends on the situation, but they're related just by a factor of 2 pi. Okay? Then finally, we have something called the wavelength. Now, is everyone familiar with the idea of wavelength? You may or may not be familiar with this. It's pretty straightforward, okay? If we just look at a snapshot of this wave, okay? You see that the fields peak at a certain point over here. Let's just take that as our sort of reference point. Then we have to kind of move along the wave a little bit before you see it peak once again at that same exact maximum value as before, right? So basically, the distance, like the actual physical distance in space, you can measure this in meters, between two peaks of the wave is called our wavelength, okay? So it's a very long wavelength, like in the case of radio waves, let's say, if the peaks are really far apart, and then it's a short wavelength if the peaks are really close together. Okay, that's just what the wavelength means. And this is the variable we use for it. What's that variable? What's that Greek letter? Lambda. Okay, so lambda, the wavelength, is the distance between the peaks of the wave. And related to that is something called the wave number. There is absolutely nothing special about this. It's just a different way of kind of writing what lambda is. This thing called the wave number is called k, and it's just 2 pi divided by lambda, okay? So it just so happens that the equations that you typically see that describe an EM wave sometimes are written in terms of k, but when you see k, you just know it's just 2 pi divided by lambda. That's it. Think about the units of this, by the way. It's radians. We have radians on top and then meters on the bottom. Okay? So radians per meter is the unit of k. All right. So all of that's just definitions. That's the meaning of the symbols that are about to pop up. So do we have any questions on the definitions? All right, so now that we've established the definitions, I'm just going to show you how this works. All right, I'm not going to derive these formulas. If you take 47, we'll do a lot more work on wave motion, where I'll actually kind of show you why these formulas work the way they do. But for now, I'm just going to give them to you, okay? It turns out if you have a sine wave, that is a wave that has a sinusoidal shape to it, you can write that wave in the following way. It's just an amplitude out front, and then you have sine kx minus omega t. Remember, omega is nothing more than your angular frequency, and k is this thing called the wave number. And what comes out front is your amplitude. So that's it. Just sine kx minus omega t with some amplitude out front. But we have separate formulas for the E field and the B field, right? Because not only do we have an electric field which oscillates between some maximum and minimum value, but we also have a B field. So for the E field, what we say is E as a function of x and t. That means the electric field not only depends on x, that's where you are along this wave, right? So this would be x equals 0. This would be some positive value of x over here. The electric field obviously is going to depend on x because it's not the same value everywhere. But it also depends on time because the field is oscillating in time as well, right? So the way we describe all that is just E naught sine kx minus omega t. For the B field, it's pretty much the same thing, but it's B naught times sine kx minus omega t. So the only difference is that we are dealing with the B field amplitude here and an E field amplitude there, but otherwise, it's the same function that's being described, okay? So that's just something I'm going to take as given. And by the way, if we were traveling along the y-axis, then instead of x going into this formula, you'd have y going into the formula. So it's pretty straightforward to generalize this, but for now, let's just think about moving in the x direction, okay? All right, so one thing I want to do is show you we have the frequency of a wave, which is how fast does it oscillate. We have the wavelength of a wave, which is how far apart are its peaks. I want to show you the relationship between those two things, between wavelength and frequency, okay? So to do that, we're going to go through a mini derivation, all right? So what I want to show you through this derivation is that if we have a wave, I'm just going to take like one cycle of the wave here. You can imagine it extends, you know, to the left and to the right, but I'm just going to focus on this one cycle of the wave right there. And you can see the distance between this point and that point is the wavelength, right? This is one full wavelength right there. That would be lambda, the distance between those 2 points. Let's imagine this wave is moving to the right at some speed, okay? This is what that would look like. Okay, so the wave's moving to the right at some speed. If you think about what's going on at this point here, it's undergone one full cycle of oscillation, right? You've seen it's basically every single point on that wave has passed through this point. So it's gone through one full cycle. So what that means is in one period of oscillation, remember a period is just how long it takes to undergo one full cycle, the wave has moved a distance that's equal to the wavelength, which is lambda, okay? So we moved a distance lambda as we underwent one full cycle. So we can think about the speed of the wave in this sense. So how fast the wave is moving. I'm going to call that c, how fast the wave is moving, is the distance it's traveled divided by the time. Okay? But in this case, we're thinking of the distance as being lambda, one full wavelength, and the time as being t, one full period. I hope you remember, we went over this in the magnetic fields lecture, that the period t is the same as 1 divided by the frequency. You guys remember that? So in other words, I have lambda divided by 1 divided by the frequency. Or in other words, lambda times f. Okay, so this is a really important relationship between the speed of an electromagnetic wave, which we call c, the wavelength lambda, and the frequency f. It says c equals lambda times f, which is a pretty simple result, but what I'm going to do in this next example is show you how to use it, okay? So, one example of an electromagnetic wave would be the FM radio signals that are broadcast by local radio stations. So if you still have a radio tuner in your car, if you still use this thing at all, you'll know that there's a certain range for FM radio, right? Your radio dial goes between about 88 and 108. But what the units that are attached to that are, which sometimes are shown on the radio dial, sometimes not, is megahertz. Okay, so that means FM radio consists of electromagnetic waves in the frequency range of 88 to 108 megahertz, and each station has its own unique carrier frequency. Okay, I'm going to give you the speed of those waves. I've given you the range of frequencies. That's right there. The speed of the waves is 3 times 10 to the 8 meters per second. You might recognize that number. If not, don't worry about it. That's just going to be the speed, okay? So my question for you is, what is the range of wavelengths for FM radio, okay? Like, what's the biggest wavelength? What's the smallest wavelength, given that the frequency range is this? So try to work it out. It's pretty simple. You can just use this formula, and you'll see the result. So let me know what the wavelength range is. Yeah, megahertz. Anyone remember what the prefix mega is in terms of the power of 10? 10 to the 6. Yeah, so that's the top end of the range. Right. And then you want to find the lower range. All right, so we have the answer. What's at the lower end of the range in terms of wavelength? Yeah, like 2.7, and then what's at the upper end of the range? Yeah, 3.4 meters. Okay, so the wavelength of radio waves, roughly speaking, is on the order of like 10 feet, which is pretty large, actually, right? If you compare that to other types of waves, it's very, very different. For example, light waves have wavelengths, or I should say visible light that we see has wavelengths that are microscopic, okay? But anyway, let's just go through the calculation. Of course, if c, the speed of our wave, lowercase c, is equal to lambda f, then if we think about lambda, the wavelength, that's just c over f, right? So for my minimum wavelength, the smallest wavelength, I want to use the biggest f value because they're inversely related. So that's c over f max. So the speed of these EM waves is 3 times 10 to the 8 meters per second. and the maximum frequency is 108 megahertz. So that's 108, 10 to the 6 hertz, which is the same as inverse seconds. So you see the seconds cancel and you get meters. This comes out to about 2.78 meters, okay? The maximum wavelength is what we get when we take C over F minimum, because again, they're inversely related. So that's 3, 10 to the 8 meters per second over 88 megahertz. That's 88, 10 to the 6 inverse seconds, and that's about 3.4 meters. So it's not that wide of a range in terms of wavelength, but there it is, okay? So any questions on that? Pretty straightforward. Okay. Okay. So now we're going to go through something of a derivation, okay? And all this derivation is done on the slide. All the slides are available to you, but I'm just going to take you through it step by step, all right? So what we're trying to do here is derive a way of calculating the speed of EM waves, okay? So how did I know in the previous example that the speed of radio waves was 3 times 10 to the 8 meters per second? It turns out there's a way to actually calculate that just based on Maxwell's equations, okay? So we'll do that right now. So what do you see here? You see a snapshot of an electromagnetic wave that's traveling in the x direction. We have the E field oscillating on the y-axis. We have the B field oscillating on the z-axis, just like this. And we're kind of zoomed in at a small portion of it, because what I want to do is look at a small portion of it, and in particular, I want us to think about this surface that you see here, okay? This is a surface that lies in the xy plane. It's basically a little rectangle, and the lengths are dx, that's the distance the rectangle takes up on the x-axis, and then dy, that's the distance it takes up on the y-axis. Okay, pretty straightforward. That rectangle forms a loop, which we can integrate around. And when it comes time to do that, I'm just going to label the sides 1, 2, 3, and 4. Okay? So, here's what I'm going to do with that. I'm just going to consider what is the integral of E dot dl around the edge of that surface, around that closed loop. Well, I'd have to break it up into 4 parts, right? I basically do the integral of E dot dl for 1, 2, 3, and 4, all separately, and see what the result is, okay? Now, can anyone tell me, I'm going to claim that when we break it down into 1, 2, 3, and 4, there are 2 of these that go to 0. Can you guys see which ones are going to 0? 1 and 3. It's not going to be 1 and 3, because in the case of 1 and 3, in 1 we're going with the E field, and in 3 we're going against it. It's actually 2 and 4 that are going to go to 0, because the path number 2, it goes perpendicular to the E field, which is along the y-axis, and path 4, it's also perpendicular to the E field, right? So if I do a dot product of E and some path that's perpendicular to E, then I'm just going to get 0 from the dot product, right? Remember, dot products, if you have perpendicular vectors, goes to 0, okay? So the second one and the fourth one go to 0 for the reason I just said. For number 1, let's think of it this way. Let's say that at the location of path number 1, the E field has some kind of value to it, which I'll call E1, right? So I'm basically just taking that value and multiplying by dy, which is the distance I travel to go across path number 1. And it's positive because my path is going along with the E field in the same direction, okay? For path number 3, that's this one over here. Now notice, this one's going against the E field. That's why there's a negative sign here. And also the E field might have a different value at the location of path number 3. So let's call that E3. But the distance we take is still dy, right? Just by the way this thing is shaped. So I have E1 dy minus E3 dy. And I can think of that, group it together as E1 minus E3 times dy. Now if you look closely at the picture, it looks like the E field is a little stronger here compared to here. It's a little bigger at 0.1 compared to 0.3. So this difference is going to be something positive. But let's call that small difference in the E field strength, let's call that dE, okay? So there's some small difference in how strong the E field is between the 2 points. We're calling that dE, and that's multiplying dy, right? So that's how I just evaluate that integral. You with me so far? I'm also going to do this. I'm going to do integral b dot dA through the exact same surface. So let's think about this, right? E dot dl is an integral over this path, okay? B dot dA is an integral through the surface, over the area, in other words, okay? So if we look at that surface right there, it has B field lines going through it, right? In other words, there's some magnetic flux, which we call B dot dA going through that surface. So I'm going to simplify this for you. I can just write this as the strength of this B field times the area of this loop, okay? And can anyone tell me what the area of that loop is? How would I express the area of that loop? Yeah, it'd be dx times dy. It's just a rectangular area. It's like length times width, right? So that's b times dx times dy. So I have the E dot dl part. I have the B dot dA part for this surface. And the reason I'm doing all that, by the way, is we have this thing called Faraday's law, right? Faraday's law says that the integral over a closed surface of E dot dl equals minus the derivative with respect to time of B dot dA. And we have both of those things for the surface, so now we can just plug them in, okay? So here's what we have. The E dot dl part is dE times dy. And then the B dot dA part is B times dx times dy. And I'm taking the derivative of this thing. Well, dx and dy are not what's changing. It's B that's changing. Okay, so we have minus dB dt times dx times dy. How can I simplify that? Just get rid of the dy's, right? Those can drop out. So the result is, if I just get rid of the dy's and I divide out the dx, I have dE dx equals minus dB dt. So in other words, the E field is changing if you move along the x-axis. The B field is changing over time, and those two things are related to each other just like this, okay? All right, we're going to do one more thing just like this, except I'm going to put my surface down here in this plane. We'll get a result, and from that we'll be able to calculate the speed of light, okay? So there we go. So same basic picture as our starting point, right? Now I want to consider a surface that lies in the xz plane. So I'm still going to call this distance dx. That's my rectangular surface, how much distance it takes up on the x-axis. And I'll call this dz. That's the distance it takes up along the z-axis. But it's kind of the same thing as before. It's a rectangular surface, so we can kind of integrate around the edge of it. And here's what that would look like. So I want us now to consider the integral around this rectangular surface of B dot dl. Okay? So now we're taking the B field and integrating over this path. Just like before, we want to think of that as consisting of 4 parts. Part 1, 2, 3, and 4. Okay? So let me just ask you, which of these parts are going to 0? Yeah, it's still 2 and 4, right? If you look at 2, that path goes perpendicular to B, so the B dot dl is going to be 0 for number 2. And it's the same deal for number 4, right? B dot dl is going to give me 0. As for the other 2, let's think about number 1. This one is going with the B field lines, right? So that means the dot product is positive. Let's say the B field has some value to it, which I'm going to call B1 at that point. If I just take B1 times the distance we move, dz, that's going to give me this part. Again, number 2 is 0 because we're going perpendicular to the B field. Part number 3, we're going exactly against the B field, which is why this negative sign appears out front. And presumably there's some different value to the B field here, which I'm calling B3. But if I multiply by BZ, I get my result, okay? So let's kind of group this up a little bit. I'm going to write this in the following way. I'm going to write this as minus, out front, B3 minus B1 times DZ. You agree we can do that? Okay, the reason I'm doing it that way is if you look at the graph, the B field should be a little bit stronger at 0.3 compared to 0.1, right? So this is a positive value, B3 minus B1. So overall, it's minus what I'll call dB. That's just the change in the B field as you move slightly from 0.1 to 0.3 times dz. Okay? All right, we're going to do one other thing here. We're going to do E dot dA, the integral E dot dA. So if you look at this surface, there will be E field lines coming through it, right? And I can definitely calculate the electric flux through that surface, which is E dot dA. Well, just to simplify, that's just whatever the electric field strength is here times the area. Just write it in that simplified way. How should I think of the area? Say again? Yeah, dx dz. Exactly. Okay, because it's a rectangular area, we're just doing the length times the width once again. So now, I'm not going to apply Faraday's law. I'm going to apply the Ampere-Maxwell law to this surface. Let me just remind you how that goes. It's the integral B dot dl equals mu naught times I enclosed. Remember, this part is real current. This is actual moving charges. We do not have any of that here. All we have is an EM wave moving through space. There's no moving currents in this location. But what we do have is this part. This is what's the displacement current, so-called. It's epsilon naught mu naught times the derivative with respect to time of E dot dA. So basically, set this to 0 because there's no actual current anywhere. Plug in this for B dot dl, plug in this for E dot dA, and we'll get our result, okay? So I have, on the left side of the equation, minus dB times dz, plus 0 for that term, like I just said. And then, okay, if I'm taking the derivative with respect to time of all of this, that's E times dx times dz. It's E that's actually changing, right? dx and dz are just distances. So we have dE by dt of dx times dz. There's a lot going on there, but we can cancel some things. What can I cancel?
dz.
Okay, cancel out dz. Let's also do this. Let's move the dx over here. So this will say now, dB dx, that's how the B field is changing with respect to x, equals minus mu naught times epsilon naught times dE by dt. Okay? So we have this result, along with the one previously derived on the other slide. If we just do a little bit of math, a little bit of calculus, I don't have to bring in any Ampere-Maxwell law or Faraday's law to do what comes next. All I have to do is do some math, take some derivatives, and we will calculate the speed of EM waves from there, okay? So I'm going to start by just showing you what we have so far, okay, because it's kind of a lot. For an EM wave that's moving in the x direction, that's our sort of test case here. We have dE dx equals minus dB dt. That's what we derived just a second ago. We have dB dx equals minus mu naught epsilon naught times dE dt. And then we also have what E and B are supposed to be equal to for a sinusoidal wave, right? We have E is given by E naught, that's some kind of amplitude, times sine of kx minus omega t. And then we have B equals B naught, that's some amplitude for the B field, times sine kx minus omega t. So, what I'm claiming here is we can use these results to get the speed of light. It's not obvious, so I'll walk you through it, how that works, okay? Let's start here, okay? Let's start with dE dx equals minus dB dt. That's the first thing we derived 2 slides back, okay? What I literally want you to do is to think of what those derivatives are, okay? If this is e, I can take the derivative with respect to x, right? If this is b over here, I can take its derivative with respect to t, okay? How's that going to go? If I take this guy and take its derivative with respect to x, what will happen? This derivative with respect to x.
It would be E naught K cosine times all that.
Yeah, you agree? Sine goes to cosine. By the chain rule, we pull out a factor of k. And that's basically it, right? It's just going to be k times E naught times cosine of all that stuff, right? What about the derivative with respect to time of b? So now look at this guy and take the derivative with respect to time. So in other words, x for that is going to be treated as a constant. We're just taking the derivative with respect to time.
Omega b naught cosine?
Yeah, so just like before, sine becomes cosine. From the chain rule, we pull out minus omega, and that's it. So here's that all put together. All right, this derivative was k E naught cosine, blah, 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 same stuff, right? This derivative, which already has a negative sign out front, is negative omega times b naught times cosine, all that stuff there, okay? This becomes really simple, right? Because what can I do? I can cancel out cosine kx minus omega t here and here. So all that goes away. We're just dealing with some constants now. Let's regroup. I can write this as E naught over B naught equals omega over K. Do we agree? Okay, so real quick, I just want to remind you that omega, if I wanted to, can be written as 2 pi f. And K is 2 pi over lambda. These are just definitions, right, that we saw earlier. So in other words, cancel out 2 pi, bring the lambda to the top. This is lambda times f. Do you agree? What does lambda times f equal to? That's the speed of the wave. That's what we call c, correct? So that's actually right there, not quite where our final result is, but it's an important result. It says that if you have an electromagnetic wave, E naught over B naught, that's the maximum E field divided by the maximum B field, that's equal to the speed of the wave, okay? But we're not done, because what we have to do is this guy now, okay? So same drill. We have dV dx equals minus mu naught epsilon naught dE dt. Just evaluate the derivatives, okay? All right, if this is B, what is its derivative with respect to x? Yeah, so K is going to be pulled out times B naught. This becomes cosine. Yeah? What's dE dt from this guy?
Negative omega e naught cosine.
Yeah, so when I take this derivative with respect to time, I get minus omega coming out times E naught and then then cosine, of the same thing. So here's all that put together, right? dB dx was K, B naught, cosine, blah, 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 right? Then on this side, we have minus mu naught epsilon naught already in the front. From the derivative, we get a minus omega times E naught and then cosine. Just like before, cosine kx minus omega t drops out. And if I wanted to rearrange things, I could do it like this, right? I could say omega divided by k. Okay, so I have omega divided by k. If I put the k down here, and then if I take the b naught and again divide it out over here, I'll have e naught divided by b naught. Okay? Then if I take these two terms and divide them out and put them over here, I'll have 1 over mu naught times epsilon naught. So just think of canceling the cosine part and rearranging everything else to give you this. Okay? Now, the reason I'm writing it this way is we can look at our previous result, right? What can I sub in for omega divided by k? Just looking at this line. That's, yeah, omega divided by k is the same thing as c, right? What can I sub in for E naught over B naught? Also c. So these two are both c squared. C squared is 1 over mu naught times epsilon naught. Okay. So if I wanted to calculate, so this is really important. If I wanted to calculate the speed of EM waves, c, right? All I need to know is mu naught and epsilon naught, which is kind of surprising because those are constants that we first encountered when we're just talking about like static E fields and static B fields. But it turns out they determine the speed of electromagnetic waves, okay? So I'm going to show the results we just derived in the following way. C, the speed of an EM wave can be thought of as E naught over B naught, or 1 over the square root of epsilon naught times mu naught. Just two different ways of writing it, but those are the results that we just got, okay? So, what I'm going to do next is show you everything we derived for the speed of an EM wave up until this point, okay? Way back before, we showed C is equal to lambda times F, okay? And then just now, we showed it's equal to E naught over B naught, or 1 over mu naught times epsilon naught. I'm interested in doing it this way, okay? Because, you see, the first two formulas depend on specifically what type of wave you're talking about, right? Different waves will have different wavelengths and frequencies, will have different E field and B field strengths, but this just depends on fundamental constants of the universe, right? So it looks like the speed of light is something that just depends on these two fundamental constants. And we can plug in the values, right? We know the values of epsilon naught and mu naught. Mu naught, 4 pi times 10 to the minus 7 Tesla meters per amp. Then epsilon naught, 8.85 10 to the minus 12 Coulomb squared per Newton times meters squared. Someone want to crunch those numbers for me? What are we getting for this result?
2.99 times 10 to the 8.
Yeah, 2.998 times 10 to the 8. If we round it off to like 3 sig figs, it's about 3.00 times 10 to the 8 meters per second. Okay, you seen that number before?
Speed of light.
That is what we call the speed of light. Okay? So, this is the speed of light. And Maxwell himself did some calculation, not exactly like what we're doing here, because we're using kind of a more modern notation for the equations. But he pretty much did this, and he determined that the speed of EM waves is equal to this value, according to the known values of epsilon naught and mu naught. But you see, in Maxwell's time, which is the mid-1800s, when he was going through this work, the speed of light had already been measured with pretty good precision, okay? So we already had an experimental measurement of the speed of light. The experiments involved basically bouncing light off mirrors, which is really far away, and measuring the return time, things like that. And there were some pretty sophisticated experiments that could get that within 1% of the known value today. So this is something that was known pretty well, and it was known to be 3 times 10 to the 8 meters per second. So if you think about what Maxwell was doing, he was calculating the speed of EM waves, and the result he got exactly matched the known speed of light, okay? So his conclusion was light is just an electromagnetic wave. The light that we see and the light that falls out of the visible spectrum is all just an electromagnetic wave of some kind or another, all right? So the fact that you can see me right now and I can see you right now just means there are electromagnetic waves entering our eyes, which our eyes are sensitive to, and we can process as some kind of image. But what do those electromagnetic waves consist of? This oscillating EMB fields. What do they come from? They come from accelerating charges. Okay, and that's true across the board. Okay? So I'm going to have you guys try this one out. You've heard the term light year before? Familiar with this? So a light year sounds like it might be a time because it has the word year in it, but it's actually a distance. Okay, a light year is a unit of distance. It's defined as the distance that light travels in 1 year. So if you just send out a beam of light in some direction and wait 1 year, the distance it's traveled after a year is what's called a light year. Okay, we know that the speed of light is 3 times 10 to the 8 meters per second, right? So based on that, I think you can tell me how many meters is equivalent to a light year, okay? See if you can work that out. We'll go through it together in a few minutes, but basically this is sort of a unit conversion from light years to meters. You can use the speed of light to do it, okay? So try it out and see what you get. It's a lot of meters, by the way, right? Pretty big distance. Okay. All right, let's go through this together. A few of you, I've gone around the room, I see you've got it, which is great. This is how it works, okay? I would just think of it in the following terms, right? One of the very first equations you ever learn in physics is speed, which I'll call v, is equal to distance over time, right? What we want here is a distance, so that's just the speed times the time. But in the case of light, we call this speed c. It's a special kind of speed. It gets its own special character. So we'll call that distance equals ct, okay? So what I'm going to do with that is plug in the known speed of light, 3 times 10 to the 8 meters per second for c. And then for t, I'm going to plug in 1 year, right? Because that's the distance we travel in 1 year, okay? That would be our time interval. But in order to get consistent units, I want to take 1 year and convert that to seconds, right? So 1 year, let's convert it to seconds. How do we do that? How about this? In 1 year, how many days do we have? 365, and then plus a little extra for leap year, but let's just say 365. Okay, in every 1 day, how many hours do we have? 24. Every 1 hour, 60 minutes, right? Every 1 minute, 60 seconds. Years, days, hours, minutes, all cancel and we have seconds. So this is basically how many seconds are in a year. It's 3.154, 10 to the 7, if you work that out, I think. So that means the distance of a light year is 3 times 10 to the 8 meters per second times this time, 3.154, 10 to the 7 seconds. What does this work out to, everybody? See, yeah, 9.46, 10 to what power? 15 meters. That's a really large distance. Okay? The nearest star is something like, I mean, obviously other than the sun, the nearest star is about 4 light years away. Okay? So, giant distance. All right, so let's now talk about the electromagnetic spectrum, okay? I want to take some ideas that I've been tossing out there and try to unify them a little bit, okay? So the electromagnetic spectrum, or EM spectrum, is just a way of classifying all the different types of electromagnetic waves that we can see if we just take a look at our universe, right? Everything from gamma rays to X-rays to visible light to radio waves is in the electromagnetic spectrum. Every single type of EM wave is in here. The way I'm showing it to you here is based on wavelength, okay? So if you go along this axis, we're basically just increasing in terms of wavelength. So the shortest wavelengths are gamma rays. Okay? Gamma rays have the shortest wavelengths, which are comparable to the size of the atomic nucleus. These are wavelengths that are really small, subatomic size. Something like 10 to the minus 14 to 10 to the minus 12 meters, okay? The next classification over is X-rays. These fall in the range of 10 to the minus 12 to about 10 to the minus 8 meters. So still microscopic wavelengths. Then we have ultraviolet, and then this tiny little slice right here, that's what we can see with our eyes. This is the visible light, okay? So we can kind of expand that because we care a lot about visible light, but it really takes up a tiny fraction of the overall spectrum, as you can see here. And the visible light spectrum goes from violet to red. So violet colors are about 4 times 10 to the minus 7 meters, or about 400 nanometers in wavelength. And as we get to the red end, we're in the range of like 7 times 10 to the minus 7 meters, or 700 nanometers. So it's a pretty small range, right, in terms of visible light, but that contains all the different colors we can detect with our eyes, okay? So wavelengths that are too short to be seen are ultraviolet. So if we had slightly more sensitive eyes to shorter wavelengths, we can see ultraviolet. On the other side of that, longer wavelengths than we can see are infrared, okay? And as we go even further, we have basically all types of radio waves here. Everything past here you can think of as a radio wave of some kind. Radar, FM radio, TV signals that are broadcast through the airwaves, shortwave radio and AM radio, those all fall here, okay? Now, these classifications, let me just ask you this. Do you think these are just something we invented to keep track of things, or is there something special about these classifications?
I'd imagine with longer wavelengths, you probably travel more readily through the air. Like they're not as inconvenienced with to travel versus like the short wavelengths.
Yeah. So let me be more specific. But what I'm saying is, you know, these classifications, like sure, there are differences, obviously, in terms of wavelength and how they might be used in technological applications. They are different, but where we draw the lines between things is kind of arbitrary, right? These are just classifications we use for our own purposes, just to keep things in a little box that we can understand, right? And of course, this part is important because that's what we can actually see, okay? So this is all given in terms of wavelength, right? In terms of frequency, you could just use C equals lambda F to see what these frequencies all are, okay? So that would be pretty easy to do. So we're gonna do this to end. Yeah, go ahead.
So in a lab with like oscillating current, can you create visible light?
We're about to get to that. So what you probably are not going to create visible light because visible light has frequencies of like many terahertz, which is kind of hard to achieve in a circuit. What you will produce using the frequencies you could easily achieve in a circuit is radio waves, which is why we broadcast radio waves at the frequencies we do, because they're easy to manipulate under those sorts of conditions, right? So actually that gets to what I was about to say here, right? So all EM waves ultimately are produced by accelerating electric charge, okay? Meaning, if I take, like forget the example I showed you where it's current running along an antenna, right? Just take a single charge Q and shake it up and down like this. That's going to send out an EM wave, okay? And that's ultimately what's happening with every single type of EM wave that we can imagine. Ultimately, there's oscillating, accelerating charge that sends out that wave, okay? But exactly how that happens is going to vary between the different types of EM waves. So for example, let's look at radio waves. Radio waves are typically just going to be produced by some sort of alternating current. If we talk about human-made radio waves, that is. You just have some kind of circuit that produces alternating current in a large antenna, and that can send out the radio wave, okay? Infrared light, where does that come from? It comes from a lot of different places, but one of them is thermal motion. So obviously anything that has a temperature to it consists of atoms which are sort of randomly jiggling around, right? Okay, that's what really heat and temperature is on the microscopic level, is atomic vibrations, okay? If you have a vibrating atom, guess what? You have a charge that's oscillating and sending out an electromagnetic wave. So if I were to put on infrared goggles and look at one of you, I could see the infrared light you're giving off, okay, just because of your body heat. Okay? There's also infrared light caused by the rotation of atoms and the vibration of atoms in addition to that. All right, where does visible light mostly come from? Most visible light is produced by electrons within atoms transitioning from one energy level to another. That's the type of accelerating charge we're talking about when it comes to visible light. Gamma rays, those are the really short wavelength EM waves. Those are generally produced by things going on in the nucleus of an atom. So the nucleus transitioning from one state to another. But all of these are just different examples of accelerating charge, okay? So the basic picture you should have when it comes to all EM waves is something like this. You have some charge, you shake it up and down, you accelerate it in some way, and that sends out an EM wave, okay? And that explains all of these different things, okay? So we're almost done. We have a little bit left to go on this. Most of the concepts have been touched on already. We'll do a lot of examples on Wednesday. But that's it for today, so I'll see you on Wednesday.